600 kilometers of carbon nanotubes stretching towards the stars. Like a celestial fishing line cast into the void, this revolutionary tether system promises to transform the economics of spaceflight from a series of explosive launches to an elegant cosmic dance. While rockets currently burn through millions in fuel to escape Earth's gravity, this offers a gentler path to orbit, one that could catch and release spacecraft with the precision of a master clockmaker. Welcome to the era of the Skyhook, a concept so audacious it sounds like science fiction, yet grounded in principles that could transform space travel as we know it. Let's start with the stark reality of our current space endeavours. The cost of reaching orbit has been the primary barrier to widespread space exploration and utilisation. In the early days, it was astronomical. The Saturn V rocket, adjusted for inflation, cost $4,000 per kilogram to low Earth orbit. The Space Shuttle, a staggering $18,000 per kilogram, with a total launch cost of $2.1 billion. These figures made space a playground for only the wealthiest nations and corporations. But the landscape is changing rapidly. As of 2024, SpaceX's Falcon 9 can deliver payloads to LEO for $2,720 per kilogram. The Falcon Heavy pushes costs even lower, at $1,500 per kilogram. These reductions have sparked a new era of space exploration and commercialization. In 2023 alone, a record-breaking 2,800 satellites were launched into LEO. However, this progress comes with its own challenges. The orbital environment is becoming increasingly congested. Approximately 35,000 objects larger than 10 centimeters are tracked in orbit, with 26,000 of these being debris. An estimated 1 million pieces of debris larger than 1 centimeter pose a threat to operational satellites. The European Space Agency reports that satellites in the 500 to 600 kilometer orbital band should expect nearly 30 conjunction events, close calls with passing satellites and debris per year. Enter the Skyhook. Picture a massive tether stretching from an orbiting station down towards Earth's upper atmosphere. This cosmic jump rope spins in perfect harmony with our planet's rotation, ready to fling payloads into the vastness of space. The concept of snatching payloads from Earth's surface has a fascinating precedent in the CIA's Fulton Skyhook system of the 1960s. This daring innovation first proved its worth in 1962 during Operation Cold Feet, when agents were extracted from an abandoned Soviet research station in the Arctic. The system used a helium balloon and harness to lift personnel who were then snatched mid-air by passing aircraft. While operating on a much smaller scale, the Fulton Skyhook demonstrated the feasibility of momentum transfer in aerial retrieval, a principle that underlies the cosmic Skyhook concept. The success of this terrestrial predecessor, which remained in use until 1996, offers a compelling proof of concept for the more ambitious space-based Skyhook systems we envision today. But how does it work, and what are the numbers behind this audacious concept? The Skyhook consists of a large station orbiting Earth, connected to a rotating tether that extends downward towards Earth's upper atmosphere. The tether's rotation allows its lower tip to momentarily match suborbital speeds, enabling it to catch spacecraft launched from Earth. Once attached, the tether's motion imparts additional velocity, flinging it into orbit or beyond. Conversely, the same system can decelerate returning spacecraft, reducing re-entry speeds and fuel requirements. The Skyhook system operates by exchanging momentum with payloads, which slightly lowers its orbit after each use. To maintain its position and rotation, the Skyhook can be reboosted using onboard propulsion systems, electrodynamic tethers, or by capturing energy from incoming payloads. A traditional rocket needs to achieve a velocity of 7.8 kilometers per second to reach orbit. That's over 28,000 kilometers per hour. But with a basic Skyhook, we're looking at needing only 4.7 kilometers per second. And here's where it gets really interesting. Advanced rotating designs could potentially reduce that to a mere 500 meters per second. That's slower than the Concorde used to fly. Let's break down a specific design proposal. Boeing's Haskell study proposed a 600-kilometer long tether, orbiting at an altitude between 610 and 700 kilometers. The tip would rotate with a speed of 3.5 kilometers per second, resulting in a ground speed of 3.6 kilometers per second, Mach 10. For a payload of 14 tons, this design called for a tether weighing 1,300 tons. That's a mass ratio of 90 to 1. The engineering challenges here are immense. We need materials with a tensile strength of about 50 gigapascals, roughly 10 times stronger than the strongest commercially available fibers as of 2024. We're pushing the boundaries of material science, venturing into the realm of carbon nanotubes and exotic composites. But the potential payoff is astronomical. The Skyhook promises to slash launch costs to potentially $100 per kilogram or even less. We're looking at a reduction in launch costs by a factor of 27 or more compared to current SpaceX prices. Now, let's talk about the cost to build this cosmic elevator. Estimates vary widely given the unprecedented nature of the project. Some early projections put the cost between $100 billion and $350 billion. To put this in perspective, it's comparable to the cost of the International Space Station, which was about $150 billion, or the Apollo program, about $280 billion. While this does seem extraordinarily high, consider the potential return on investment. If we could reduce launch costs by a factor of 25 or more, the Skyhook could pay for itself many times over in the long run. The space industry is already taking steps to address the challenges that a Skyhook system would face. ESA's Zero Debris Charter, launched in 2023, aims for debris neutrality by 2030. The number of payloads deorbiting has increased every year since 2019. In 2023, more than half of rocket bodies re-entering the atmosphere did so in a controlled manner. These efforts to clean up our orbital environment are crucial for the feasibility of a Skyhook system. Looking ahead, the future of space access is bright. The National Reconnaissance Office expects launch costs for larger rockets to fall well under $100 million per launch. Small satellite launches could drop to $10 million or less. These reductions are enabling new architecture approaches, including proliferated constellations and diversified satellite sizes. Technological advancements are reshaping the space industry in profound ways. The miniaturization of satellite components has led to dramatic reductions in payload mass. For instance, CubeSats, weighing just 1 to 10 kilograms, can now perform tasks that once required satellites weighing hundreds of kilograms. This miniaturization, coupled with improvements in digital technology, has enabled more capable and efficient spacecraft. These advancements set the stage for the development of Skyhook systems, not just around Earth, but potentially on the Moon and Mars as well. Here's how a network of Skyhooks could form an interplanetary highway system. On Earth, we'd start with a 600-kilometer long tether, orbiting at an altitude between 600 and 700 kilometers. On the Moon, with its lower gravity, we could construct a shorter Skyhook, perhaps 300 kilometers long. It would require less robust materials due to reduced stresses, and could potentially be constructed using resources mined on the Moon. A Martian Skyhook would be an intermediate length, around 450 kilometers. The possibilities of this interplanetary transport system are massive. A spacecraft could be launched from Earth's Skyhook, caught by the lunar Skyhook, then flung towards Mars. This method could reduce fuel requirements by up to 90% compared to traditional rockets. Travel time to Mars could potentially be reduced from 6 to 8 months to 3 to 4 months, revolutionizing our approach to interplanetary exploration. The implications for space exploration and industry are staggering. In orbital manufacturing, microgravity enables unique processes in pharmaceuticals, metallurgy, and optics. Axiom Space plans to launch a research and manufacturing facility to the ISS by 2026. By 2030, entire satellites could be manufactured in orbit, as proposed by Airbus. Space-based solar power becomes a tangible possibility. Large-scale solar arrays could be constructed and assembled in orbit, with energy beamed back to Earth using microwave transmission. A single kilometre-wide array could generate gigawatts of continuous power, potentially revolutionising our approach to clean energy. For scientific research, the Skyhook opens up new frontiers. Large space telescopes like the proposed LUVOIR, with its 15-metre primary mirror, become feasible. Swarms of small satellites for Earth observation and climate monitoring could be deployed with unprecedented ease and frequency. The road to implementation of Skyhook systems is long, but progress is being made. Boeing's Hastel study confirmed the technical feasibility of the concept. Advances in materials science, such as carbon nanotubes and graphene, are bringing us closer to the required material strengths. As we continue to push the boundaries of what's possible, the Skyhook concept moves from science fiction to potential reality, offering a more efficient and sustainable approach to space exploration. A Skyhook would be a technological marvel, as well as a testament to our unyielding drive to explore. As we contemplate this cosmic ladder, we're reminded of the words of Konstantin Tsiolkovsky, the father of astronautics. The Earth is the cradle of humanity, but mankind cannot stay in the cradle forever. The Skyhook may well be our first step out of that cradle into the vast cosmic ocean that awaits us.